Good morning, everybody. This is Jesse Crawford with Tarleton State University, and we are now ready to go into Chapter 4 in the Foundations of Mathematics course. Today's video will be about Section 20, which covers a few new proof techniques. We're going to talk about proofs by contrapositive, proofs by contradiction, and then also a few proof templates for showing that sets are empty and for showing that mathematical objects satisfying certain conditions are unique. So the first thing we're going to discuss today is proof by contrapositive. This is a proof technique that comes into play when we want to prove a statement of the form if A then B. And this is actually something that's come up pretty recently for us. We had an if then statement, and we sort of recalled from chapter 1 that an if then statement is equivalent to its contrapositive. A contrapositive, as a reminder, is what happens when we reverse the order of these statements and negate each one of them. And because the contrapositive is logically equivalent to the original if then statement, proving the contrapositive is equivalent to proving the original statement. Of course, to prove this if then statement, we just need to assume the statement on the left, deduce the statement on the right, which has the following template down here, assuming not B and deducing not A. Well, let's see an example of this. So in this proposition, we are letting R be an equivalence relation on a set A, and we're letting A and B be elements of A. We want to prove that if A is not related to B, then bracket A intersect bracket B is empty. Now, if you think about how you would prove this statement with a direct proof, you would just assume this. You would just assume that A is not related to B, and then you would try to show that bracket A intersect bracket B is empty. But this can be a really difficult way to proceed with a proof because if you just start by assuming that A is not related to B, it's like you just don't really have much to work with, and it's really difficult to make progress in this problem. So the approach that we're going to take instead is we will look at the contrapositive. Of course, the contrapositive involves us switching this order and negating both parts. So we'll switch this part to in front and we'll negate it. We'll put a not equal sign here, and we'll take this statement here, move that to the end, and also negate it. So instead of saying A and B are not related, A and B are related. Now, how do we prove this contrapositive? Well, this is our proof template, right? We need to assume the thing on the left and eventually get to the thing on the right. So we start off by assuming that bracket A intersect bracket B is non-empty. Of course, that means there exists some element C that is in both of those equivalence classes. That's just what an intersection means. And if C is in bracket A and C is in bracket B, then that means that C is related to A and C is related to B by definition of equivalence classes. And of course, at this point, we can start using properties of the equivalence relation R. We can use symmetry of R to change the order of C and A here. Now we have A is related to C, but this is another example of a chain. We have A is related to C, we have C is related to B, and therefore A is related to B by transitivity of R. And so we're done with this proof. So to kind of do a recap, we wanted to prove this if-then statement. We started off by simply writing the contrapositive down. And to prove this contrapositive, we just need to assume the thing on the left, deduce the thing on the right, and that's what we've done here, right? We've assumed this, and we've ultimately deduced this. And so we have proven the contrapositive is true, but that proves the original statement we were interested in is also true. All right, let's move on to the next proof technique, which is going to be proof by contradiction. But before we can really get into that, there's going to be some additional definitions that we need. This first definition is the definition of a rational number. And I'm sure most of you have seen this before, but I do want to make sure everyone's comfortable with this definition before we move forward. So this says let x be a real number, then x is a rational number if x is equal to a divided by b, where a and b are integers. So yeah, basically a rational number, as we all know, is any number that can be written as a fraction where the numerator and denominator are both integers. And if x is not rational, then it's irrational, right? It's a pretty self-explanatory idea. So a quick example of this would be the number 0.75. Is this a rational number? And the answer is yes, it is, because we can write 0.75 as, as an example, we could write it as 9 divided by 12, and 9 and 12 are both integers. Now, I'm sure that most of you watching right now are thinking, man, why did you choose 9 over 12? That seems kind of like a strange choice. And it really is a strange choice. The thing that makes this choice strange is the fact that it's not completely reduced. And being able to write a rational number as a fraction that's fully reduced is an important idea that's going to come up in a proof later. So let's actually formalize what we mean by that. So um, what we can say is if we let x be a rational number, then not only can we write x as a over b for just some arbitrary integers a and b, but we can specifically choose a and b to have the property that the greatest common divisor between them is 1. So this kind of weird choice I made up here, this doesn't actually satisfy this condition because the greatest common divisor between 9 and 12 is 3. In other words, it's not fully reduced because we can cancel a 3 out. We do want the capability of writing it in such a way that this GCD is 1. So the example, of course, that we would use for this one is if x is 0.75, then we can write x is 3 divided by 4. And now 3 and 4 are integers with a GCD of 1. This idea is going to be helpful for us in a proof that we're going to do in a moment. Now, another property of integers that we haven't really had a chance to discuss yet is this nice little property of prime numbers. This says let p be a prime number and assume that p divides ab, where a and b are integers. It turns out in this situation that p must either divide a or b. And again, let's just look at a quick example of this. We're not going to prove this. This is really not that hard to prove, but it just requires quite a bit of machinery that we haven't developed that, you know, it's kind of like a side topic, and you will eventually see this kind of material in either a number theory course or an abstract algebra course. You will get to this, but just as a few quick examples to get our head around this idea, one example might be like 3 divides 2 times 9. So 2 times 9 is 18, and of course 3 does divide 18. And so we might ask ourselves, well, is it really true that 3 divides one of these numbers on the right? And of course it does, because it does divide 9. So this is actually an example where we have a prime number dividing a product, and that prime number does divide one of the factors in the product, because it has to. That's what this proposition says. But if we have a composite number dividing a product, like here 6 divides 2 times 9, which again is true because 2 times 9 is 18, does it necessarily follow that 6 divides 2 or 6 divides 9? And of course, the answer to that is no. That doesn't actually work. So the property that's given in this proposition does work for prime numbers. It does not actually work for an arbitrary integer p. Okay, well, with those preliminaries out of the way, we're now ready to talk about proof by contradiction, which is our next proof technique. So the setting for this is that we want to prove some statement A, and the method that we use is we just assume that A is not true. We assume the negation of A, and we show that this leads to a contradiction. Now, a desirable property of the logical structure that we use in mathematics is that there are no contradictions. So for example, we wouldn't say that 2 plus 2 is 4 and that it's also the case that 2 plus 2 is not equal to 4. That's just nonsense. Like 2 plus 2 either has to be 4 or it has to not be 4. We need a mathematical logical system that doesn't have contradictions in it. And therefore, if an assumption that we make leads to a contradiction, that assumption must be false. And this gives us a way to prove things using contradiction, because basically the way this works is you want to prove that A is true, so you assume the negation of A, and then this leads to a contradiction. Well, that means the negation of A is false, and that means the original statement is true. And one of the most classic examples of a proof by contradiction is the proof that the square root of 2 is an irrational number. So let's think about how that's going to work in this setup. We want to prove square root of 2 is irrational. So the way we're going to do this is we'll assume that the square root of 2 is not irrational. In other words, we'll assume that it is rational, and we'll show that this leads to a contradiction. So let's go ahead and get into that on the next slide. So again, this is the template. We're going to start off by assuming radical 2 is rational, and eventually we're going to get a contradiction, and that will actually prove that our original assumption is false, so square root of 2 actually has to be irrational. But let's just jump into this. So because the square root of 2 is a rational number, it can be written as a fraction a over b, where a and b are both integers. That's what we saw a couple slides back. And we also talked about the idea that we can force the numerator and the denominator in this fraction to have a GCD of 1. This is actually going to be important in a second. All right, well, if radical 2 is a over b, we can do a bit of algebra using appendix D. Basically, we can square both sides and then multiply both sides by b squared and get this equation. But you'll notice this equation implies that 2 divides a squared by definition of divisibility. Now, another way to think of a squared is that a squared is a times a. Now, I'm actually going to scroll back quite a bit here. I want to just bring this property up. What does this say? This says that if a prime divides a times b, then either that prime divides a or that prime divides b. So, in this case, we have the prime number 2 divides a squared, but a squared is a times a, right? So if 2 divides a times a, then that means that either 2 divides a or 2 divides a by the property we just looked at. But that's redundant. What that really means is that 2 has to divide a. And again, this is a property that follows because 2 is a prime number. Okay, so once we know that 2 divides into a, well, we can rewrite a as 2 times c for some integers c and z by definition of divisibility. And now we can take this expression 2c and plug it back into this equation up here. That will give us that 2b squared is equal to 2c quantity squared. Go ahead and do the algebra here, and we'll reduce this a bit. We'll take both sides and divide them by 2, and we now have b squared is equal to 2c squared by appendix D. But the funny thing at this point is this proves that 2 is dividing b squared. But again, playing the same game that we used a minute ago, if 2 divides b squared, then 2 has to actually divide b because 2 is prime. But now we know that 2 divides a and 2 divides b. That means 2 is a common divisor of a and b. But that means the greatest common divisor of a and b must at least be 2. It could even be bigger, in this hypothetical. But the GCD of a and b would have to be at least 2. But up here we also assume that GCD of a b is equal to 1, and that's a contradiction. So again, a contradiction is two statements that are sort of mutually inconsistent, like two statements that cannot simultaneously both be true. So the statement that GCD of AB is 1 and the statement that GCD of A comma B is greater than or equal to 2, those can't simultaneously be both be true. So that's what we mean by a contradiction. Now, again, once you have a contradiction, what does that do for you? Well, what that really says is this original assumption up here can't be true. If this assumption leads to a contradiction, this assumption cannot be true. And so the way that we finish this proof is we just say, this is a contradiction which proves the original assumption must be false, and therefore the original assumption that square root of 2 is a rational number is false. Well, that means that the square root of 2 is an irrational number. So that's a really nice proof by contradiction, and again, one of the most sort of iconic examples of a proof by contradiction. Okay, let's go to our next slide here. We're going to move forward and look at another situation where proofs by contradiction are used. But before doing that, I wanted to remind you guys of this little idea here. This is a truth table. You'll notice that we have two Boolean variables A and B. And as usual, we have a truth table where A is true, true, false, false, and B is true, false, true, false. And I'm looking at the truth table for A implies B. And we have this here. We're also looking at the truth table for not A or B, and we can kind of go through all of the calculations here and show that the truth values in this column right here are the same as the truth values in this last column. And what that proves is that this expression A implies B is logically equivalent to not A or B. And I believe this was actually a homework problem back in chapter 1 that you all demonstrated. So those are equivalent to each other. Now, why are we interested in this? One thing that we might want to do is take the Boolean expression A implies B and negate it. We were just talking about proofs by contradiction, and the first step in a proof by contradiction is to look at the negation of what you're trying to prove. So let's say the thing we're trying to prove is A implies B. Well, we need to negate this, right? But negating this is the same thing as negating not A or B, because again, A implies B is equivalent to not A or B. But how do we negate an or statement? We have a little property of logic called De Morgan's law. De Morgan's law says that if you're negating an or statement, you can essentially convert it into an and statement. and then negate the first expression and the last expression. So we're going to negate not A, we'll get not A, and we'll negate B and we'll get not B. And again, this or is going to turn into an and statement. And of course, the negation of a negation is just the original statement, and there we go. So what we've proven here is that the negation of A implies B is the same thing as A and not B. And this really makes sense if we think of some of the examples that we've used for if-then statements. Like one example I've used is that, if my nephew mows my lawn, I'll pay him $20. But what would the negation of that be? The negation of that would be that my nephew mowed my lawn and then I didn't pay him, right? That's how you contradict the statement that A implies B, is you find an example where A is true and B is not true. So with all of this in mind, let's go to the next slide and we'll talk about doing proof by contradiction for if-then statements. So again, the setting here is we want to prove a statement, but we're going to assume right now that it's specifically of the form of an if-then statement, A implies B. So what is the proof template? Well, to do a proof by contradiction, you assume that the thing you're trying to prove is not true. In other words, you assume the negation of what you're trying to prove. But the negation of A implies B is A and not B. That's what we just saw on the previous slide, right? So we're going to assume A and not B, and again, show that this leads to a contradiction. So as a quick example of this, let's just look at this proposition here. This says if n is an integer and 4 divides n, then 4 does not divide n plus 2. What would be a nice way to prove this by contradiction? So it's an if-then statement, right? It's if this statement holds, then this statement holds. So the way we do a proof by contradiction is we assume this part and we assume the negation of this part. So we are going to assume that n is in z. We are going to assume that 4 divides n. And the negation of 4 does not divide n plus 2 is that 4 does divide n plus 2. So we're just going to assume that all of this is simultaneously possible. We're going to show that leads to a contradiction. And that means that this cannot all be possible at the same time, so that whenever this is true, this must not be true. That's how we're going to approach this. Okay, let's go ahead and take a look at this. So again, we're assuming that n is in z and 4 divides n, and that 4 divides n plus 2, and we want to show this leads to a contradiction. So again, we're assuming this stuff is true, and we're assuming the negation of this, right, which is that 4 does divide n plus 2. All right, well, we can just write down what does it mean for 4 to divide n? That means that n is 4a for some a and z. What does it mean for 4 to divide n plus 2? That means that n plus 2 is equal to 4b for some b and z. And then we can basically take this second equation and subtract the first equation from it. Again, Appendix D basically allows us to do this. So we now have n plus 2 minus n is 4b minus 4a. These n's are, when we take n minus n, we're going to get 0. 0 plus 2 is 2. And then we can also use the distributive property to factor out a 4. And we have 2 is equal to 4 times b minus a by Appendix D. And the thing is, this actually implies that 4 divides 2, right? We have 4 times an integer is equal to 2. But of course, that's nonsense because we know 4 can't divide 2. We know 4 does not divide 2 because there does not exist an integer c such that 4 times c is equal to 2. We can simply systematically check every possibility and show this, right? There's just no possible way that you can take 4 times an integer c and get 2. So this is a really great example of a contradiction. This says that 4 does divide 2. This says that 4 does not divide 2. Those two statements directly contradict each other. That's what we mean by a contradiction. And because this contradiction is here, that means the original assumption cannot be true, and therefore this proposition must be true. Again, this assumption is the negation of this proposition. If this assumption cannot be true, then this negation can't be true. That means the original statement must be true. All right, guys, so the next type of proof template we're going to look at today is proving that a set is empty. Now, we're fundamentally going to use a contradiction approach on this. We want to prove that a set is empty. One of the easiest ways to do this is to just assume it's not empty, and again, show that leads to a contradiction. So the example we're going to look at here is, let's let capital X be the set of all integers x such that x is even, and capital Y be the set of all integers x such that x is odd. And we're going to prove that x intersect y is empty. So of course this will just prove a very simple fact that it's impossible to be even and odd at the same time. That's not possible, right? So how are we going to prove that x intersect y is empty? Well, this proof template basically says, let's just assume that x intersect y is not empty and show that that leads to a contradiction. So we'll go ahead and do that on the next slide. Let's assume x intersect y is not empty. We want to show this leads to a contradiction. Well, if this intersection is non-empty, there's got to be something in there, right? So there must exist some x such that x is in capital X and x is in capital Y. But that means that that x is even and that x is also odd, because that's the definition of these sets, capital X and capital Y. If x is even, then 2 divides x, and also that means that x is equal to 2a for some integer a. And if x is odd, that means that x is equal to 2b plus 1, because that's the definition of odd. And of course, at this point, we can say, because x is 2a and x is 2b plus 1, that actually means that 2a has to be equal to 2b plus 1. And we can do some algebra, move this term to the other side, factor out 2. We have 2 times a minus b is equal to 1. Basically, Appendix D allows us to perform these algebraic operations. And this implies, this is very similar to the previous proof we looked at, this implies that 2 divides 1, but that's not true. We know 2 does not divide 1 because there does not exist an integer c such that 2 times c is equal to 1. So again, we have a contradiction. This is impossible, and therefore this original assumption that x intersect y is not empty is false, and that means that x intersect y must be empty. Okay, so this is the last type of a proof technique that we're going to look at today, and it is, how do we prove that an object is unique? There's situations like this that occur in mathematics where you have some set of conditions and you want to prove that something satisfies those conditions, but you often want to prove that the object that satisfies those conditions is unique. In other words, there's not more than one object satisfying it. So in order to prove uniqueness, what you're going to do is assume that x1 and x2 are both objects satisfying the conditions. And then if that logically implies that x1 is equal to x2, then that means there's only one, right? Because if there were 2 different ones, this logical consequence would not actually hold. So that's the method we're going to use to prove uniqueness. Now, as a quick example of this, let's look at this proposition. This says, let m and b be real numbers where m is not 0. Then we want to prove that there exists a unique x in the real numbers such that mx plus b is equal to 0. So this is a notation we haven't seen yet. Of course, we've seen that this backwards e is an existential quantifier, but this exclamation point means unique. So the way that you read this is, this says there exists a unique x in R such that mx plus b is 0. And of course, the fact that m is not 0 here is really important for this to work. All right, what's our proof template going to look like? Well, whenever you're trying to prove the existence of a unique object, there's generally going to be 2 steps. The first step is to show existence. Now, we already know how to show existence. The way we prove an existential quantifier is we simply define an object that's going to satisfy this property. And you can do some scratch work and very easily show that the choice of x that works is x is equal to negative b over m. So we simply define this specific choice for x, and then we just show that it satisfies this condition, right? So we just write mx plus b is equal to m times negative b over m plus b. We're just taking this value of x and plugging it in here. Appendix D allows us to do the algebra here. M times its multiplicative inverse is going to give us 1. 1 times negative b is negative b. And then negative b is the additive inverse of b. So when we add these together, we get 0. So all of this follows from Appendix D. And then we're basically done at that point, right? We've shown the existence of a variable x that satisfies this equation. So now we're ready to show uniqueness. And again, our proof template for uniqueness is to assume that x1 and x2 are 2 real numbers that both satisfy this condition. So you see that x1 satisfies the condition that mx1 plus b is 0, and x2 satisfies the condition that mx2 plus b is 0. Let's see if we can deduce that x1 is equal to x2. That's what our goal is. So we will simply set these equal to each other. You know, if mx1 plus b is 0 and mx2 plus b is 0, then it follows that these are equal to each other since they're both equal to 0. And now we can simply subtract b from both sides. And again, we have b plus negative b is 0, and 0 plus anything is itself. And then we can multiply both sides by the multiplicative inverse of m. And so this is what we have, and we end up getting x1 is equal to x2 by appendix D. All right, guys, so that was it. Again, pretty nice and efficient discussion for this section in the book. And here are the homework problems that correspond to this section. As always, just let me know if y'all have any questions. Feel free to reach out by email or post a question in Canvas. But I'll see you next time.